Okay, in this video I'm just doing a verbal explanation of some of these questions in this worksheet that you were given on position, velocity and acceleration graphs. Question 1, we can see that the graph shows the position, so it's x displacement of the particle versus time, and the period of motion here is, or the length of motion, the time taken is 2 pi seconds, the period is pi. Okay, it looks like it's a sine curve, but you don't really need that. But when is the particle at the origin? We can see it's when time is 0, pi on 2 pi, 3 pi on 2, and 2 pi seconds. It's stationary when the velocity, remember velocity is gradient of the tangent to the curve, so it's stationary between 0 and pi and 2, halfway between, which is at pi and 4 seconds, and then from a half to 1, which is 3 pi on 4 seconds. It's also stationary here, halfway between 1 and 1.5 pi, which is 5 pi and 4 seconds, and this would be halfway between 1.5 and 2 pi, which is 1 3/4, which is 7 pi and 4. So it's pi and 4, 3 pi and 4, 5 pi and 4, 7 pi and 4 seconds. And that's got to do with the gradient of the tangent to the displacement curve being 0. How many times does the particle change direction? Well, the velocity is positive here, so it's travelling to the right. Now its velocity is negative, travelling to the left, travelling to the right up there, travelling to the left, travelling to the right. So we've got one change of direction here, another one, 2, 3, 4. 4 changes in direction. Describing the motion of the particle. Particle starts at the origin, it then moves 2 meters to the right of the origin, takes, in the first pi and 4 seconds, it takes pi and 4 seconds to do that, it then stops, turns around, gets back to the origin at pi and 2 seconds, and then in another pi on 4 seconds, it ends up at 2 meters to the left of the origin, and then in another pi and 4 seconds, it's back at the origin. So basically it oscillates between 2 and -2, and that complete motion from 2 to -2 takes pi seconds. Okay, so it starts at the origin and it then moves to 2 meters to the right of the origin, then goes back to the origin, moves to 2 meters to the left of the origin, and then back to the origin, and that cycle takes pi seconds, and then it repeats. And sketch the particle's velocity against time. You can see you've got positive velocity there, 0 velocity, negative velocity here, all negative, 0 velocity, etc. Just look at the solutions for that, and you'll be fine. Okay, so it's just, well, I can just put it up, just one sec. Velocity against time, we can see here velocity is not 0, but it's positive, and it's a fairly big value. Here the velocity is getting smaller, and here the velocity is 0. So if you look straight down there, if I actually stretch this graph out, 7 pi and 4, yeah, it's about the same spot. So if I see here at pi and 4, the velocity is 0, which is under there. Here at pi and 2, that's the maximum negative velocity, which is down here. This is at 3 pi on 4, again, gradient here is 0, so here we've got 0 velocity. Here we've got a positive velocity, and it's the maximum at pi. So that position here relates to that. Here we've got positive velocity up until 5 pi and 4, but that's the maximum positive velocity, that's why it's coming back down. Here the velocity is 0. Here all that velocity is negative, indicated by this, but with the greatest negative velocity at this point, indicated by that. At 7 pi and 4 here, we've got a stationary point there, which is 0 velocity, and here gradient positive, velocities positive here. Okay, just putting that out of the way. Now for part 2, it says sketch the velocity of the particle. Now the following graph shows the velocity, sketch the acceleration. Positive velocity, the gradient of that velocity, and its constant velocity, its gradient 0. So the gradient of that is 0, so therefore the particle's acceleration, the graph, is just like this here. That's the acceleration graph just there, okay? Now, the second part of the question, so acceleration is 0, from time 0 to time t. Now, for the next part of the question, how far did the particle travel in the first 10 seconds? Well, if the particle's travelling at 8 meters per second, so every second it travels 8 meters, and if it does that for 10 seconds, then it will travel 8 times 10, which is 80 meters per second. But another way you can do that, if you notice, if I've got 10 seconds here, okay, actually I'm going to come to my screen in a minute. I'm just going to draw this and just talk about this now. So, okay, I'll just move all. Okay, here's the velocity curve, 8 meters per second. And let's say it travels at that speed for 10 seconds. Now we know that distance, if it's 8 meters per second for 10 seconds, that it will travel 8 times 10, which is 8 meters per second times 10 seconds, it'll travel 80 meters. But there is another way of doing this. Notice that x, or displacement, is the integral of the velocity curve. So therefore, it's actually the area underneath the velocity curve between time 10 and 0. So integral from 10 to 0 of v dt. Now v happens to be 8, okay? So integral of 8 from 10 to 0. Integrating 8 is 8t, substituting in 10 and 0, and we get that the distance travelled is 80 minus 0, which is 80 meters. So we've done that two ways, just doing it by common sense, 8 meters per second for 10 seconds. It travels 8 meters every second, and it does that for 10 seconds. You'll travel 80 meters. Or this displacement, distance travelled, is the area under the velocity curve. So distance travelled equals the area below velocity curve. Of course, enclosed between the curve and the x-axis, okay? Now for question 3. Might be a minute. Okay, it says that a particle started at the origin, so question 3, and travelled with constant velocity. So I'm doing a velocity curve, okay? Started at the origin, travelled at constant velocity of 16 meters per second for 12 seconds. So I'm just going to go, this is 12 seconds, this is 16 meters per second, okay? So this is the velocity graph, okay? It then experienced a constant acceleration for 5 seconds, so we're going up to 17 seconds. And then the particle, so if it's a constant acceleration, then the velocity must be a graph like that, because that's constant acceleration means constant gradient of velocity curve. So if you differentiate that, you will get a constant value. So for example, if you look at this and ignore the rest, that might be a straight line, for example, v equals 2t or something. Now, when you differentiate that, you get v equals 2, for example. So that would be this straight line portion of the velocity graph does represent constant acceleration. That happens for 5 seconds. And then the particle continued with a velocity of 36 meters per second. Now, I haven't really drawn this to scale, all right? It then travelled with a velocity of 36 meters per second for another 8 seconds. That would take us up to 25 seconds. Now, we've just sketched the velocity graph for that, okay? And the next part of the question says calculate the total distance travelled. Now, we know from the last part, question 2, that distance travelled is the area below the velocity curve. So you can tell that by just looking here as well. If it travels 16 meters per second for 12 seconds, then the distance travelled, so the distance travelled, from t equals 0 to t equals 12 seconds is 16 times 12, because that's just the area under the curve here that I've shaded area 1. So 16 times 12 is 192 meters, part 1. Let's just do this part here, part 2. The distance travelled from time is 17 to 25 seconds. Well, this length here is 8 and that's 36, so it's 36 times 8. So basically it's travelling at straight line graph here, 36 meters per second for 8 seconds, so 36 times 8 is 288 meters, and that's the area under that curve as well. All right, so you can do it common sense method, 36 times 8, or it is the area under the curve. Now, area 3, have to find the area under that curve. So the distance travelled from time equals 12 to 17 seconds. Now, this area here is a trapezium. So it's going to be h on 2, so it's 5 on 2, a plus b. Your a is 16 and your b is 36. So that is 16 plus 36 times 2.5, and that's 130 meters. So therefore the total distance travelled is 192 plus 288 plus 130. So 130 plus 192 plus 288 is 610 meters. Part of the question is to sketch a graph of the particle's position at time t. Now we know that the particle started at the origin and travelled with a constant velocity of 16 meters per second for 12 seconds. So the velocity was constant, and so the grade, so that means it's travelling when we're drawing the x curve, and I'll just bring that up now, that it will be going up at the same amount over time. So I'm just going to do that now. So here I've got displacement versus time. So for the first 12 seconds, it's got a constant velocity, and it's travelled in those first 12 seconds 192 meters. So actually I really need to get this scale correct. We did travel 600 over altogether. So if that's 0, 1, 2, 3, 4, 5, 6, 610 is going to be up here somewhere, 610 meters. That's where we're going to finish. So 192, roughly about there, straight line graph. First 12 seconds, travels 192 meters. I don't need to put that meters because I can just write meters somewhere else. In 12 seconds. And then over the next 5 seconds, probably not drawn very well to scale, and then we've got the 25-second mark as well. In the next 5 seconds, it does travel with constant velocity, and actually no, it's not constant velocity. It says it had the constant velocity for 12 seconds at 16 meters per second. It then experienced constant acceleration for 5 seconds. So it then accelerates for 5 seconds, and then it continues with constant velocity after that. So it experiences constant acceleration. So it's going to be speeding up for 5 seconds. Now in that time it travelled 130. So I know I haven't drawn this very well. So 192 plus 130, I better mark it out on the page first. It gets to 322, that's 200. 322 is about here, so I'm going to draw that again. So over the next 5 seconds, if this is 12, this would be about 17 there. So it goes from there to 322. Best off marking out your positions first, and then showing that that's concave up, okay, because it's accelerating. And then again from 17 to 25 seconds, probably about there, it then travels, actually you want these to be fairly, you know, let's say that's 5, that's 10, 12, that might be 15, that might be 20, that's about right, 25, but I'd be marking this out with a ruler, not like what I've done. It then travels 288 meters over the next 8 seconds, so it ends up at 610. Okay, now this is traveling here at 36 meters per second. This was only 16 meters per second. Of course, the gradient of this is going to be steeper than that. So you just got to make sure of things like that. But if the scale is drawn correctly, it will look like that. Okay, and that's therefore your distance time graph. But to make this bit more pronounced here, you might just want to go like this or something. Just showing that it's concave up. Okay, because you don't want there to be any confusion there that that is a concave up. Okay, and you can even write it there, just say concave up here or something like that. All right. Okay. Now for question 4, it says this graph shows the particle's position. So this is a displacement versus time graph. And write down the time when the particle's stationary. Now stationary will be when velocity is 0, and that's when dx dt is 0, so it'll be stationary here when the gradients are 0. At 10, 20, 30, actually be stationary as well at time 0, and at 40 seconds. And when is the particle at the origin? Well, that's nice and easy. It's at these points that I'm pointing to here. Looks like 5, 10, no, looks at 5, 15, 25, 35 seconds. When does it have a positive velocity? It's when the gradient's positive, so between 0 and 10 seconds, between 20 and 30 seconds. When does it have a negative acceleration? Now this is the displacement curve, and the second derivative is acceleration, so when is it concave down? See, I can see concave up here up to 5 seconds, concave down from 5 to 15 seconds. So negative acceleration from 5 to 15 seconds, then we've got concave up here, and again concave down from 25 to 35 seconds. Then you have to find the total distance travelled. Now this is a displacement curve. So distance travelled, it starts at -8, ends up at +8, goes back down to -8, goes up to +8 and down to -8. So it's travelled 8 up, no it hasn't. It's travelled 16 up, 16 back down because it's 8 and 8. So 16, another 16, 16 and another 16. That's 16 times 4, which is 64 meters. And sketch the particle's velocity. Again, we know we've got 0 velocity, positive velocity, 0 velocity, negative velocity, 0, positive, 0, negative. Also here, this is the maximum of the positive velocity. This is the sort of the maximum negative velocity. So it'll be the curve will be turning back up. I'll just put that graph there now for you. Here we can see we've got a positive velocity. Sorry, 0, gradient 0, up here gradient 0. So this is where velocity 0 at 10 seconds. We can see that velocity 0 at 0 seconds, velocity 0 at 20. And at 30 and at 40. So velocity 0 at all those. Then we see positive velocity from 0 to 10 and the maximum velocity, positive velocity, steepest part of the graph here occurring at 5 seconds. So that's why here's the maximum bit there at 5 seconds and it comes down. Again, negative gradient. So we've got negative velocity from 10 to 20. Positive gradient from 20 to 30 with the maximum at 25, positive values. And negative from 30 to 40. And now for question 5, again, we've got a velocity time graph. It says, what is the initial velocity of the particle? And that's pretty straightforward. It's 2 meters per second when time is 0. Sketch the graph of the acceleration. Well, we've got a constant velocity, but with this one, we can actually work out what the acceleration is. Like, remember, acceleration is the gradient of this curve. So the gradient is rise over run. Looks like you're rising from 2 to 10, which is 8. So it's 8 over, from 0 to 4 is 4. So the acceleration is 8 over 4, which is 2 meters per second per second. So the acceleration graph should show that. the acceleration graph should look like this, but I believe that this should be a 2 because you can actually work out. Remember that acceleration is the gradient of that velocity curve, and the gradient of that curve is 8/4, which is 2 meters per second per second. So this should be a 2, but it is constant. Notice the gradient is the same all the way along. Now, for the next part of the question, part 3, it says calculate the total distance covered by the particle during the first 4 seconds. Now, I'm just going to bring up my screen here, and we'll just do distance travelled here. So, distance travelled is the area below the velocity versus time curve, and that is a velocity curve. So here's our velocity curve, and this is 4, this is 0, that's 2, and this is 10. So therefore this height here is 10, and this distance here is 2, and that distance there is 4. So therefore the distance travelled equals the area of that trapezium. It's the area below the curve from 0, which is area of trapezium, which is the h on 2, so h is 4, so it's 4 on 2, a plus b, that's 2 plus 10, so therefore it's 2 times 12, which is 24 meters. Okay, so that question's done. Now for question 6, and it says that a particle's velocity, v meters per second, at time t seconds is shown on the graph. If you look here, it starts off with a negative velocity, negative 12 meters per second. So it's traveling in the negative direction. And here, after 6 seconds, velocity is 0, so it stops. And then from 6 seconds onwards, the velocity is positive, and so it's traveling in the positive direction. So it says, first question, when is the particle stationary? Well, it's at time 6 seconds. Describe the particle's acceleration. Now, this is a constant velocity. So sorry, no, it's not a constant velocity. The velocity has a constant gradient. The gradient's the same. Now, acceleration is dv dt, which is the gradient of the velocity curve. Now, that gradient is constant. It's the same gradient all the way. Therefore, the acceleration is constant. And because the gradient's positive, it'll be a positive constant acceleration. Okay, so it'll be accelerating at a constant rate in the positive direction. And it says initially the particle is at the origin. Sketch its position x from the origin at t seconds. So if you've got v and you want x, so v, we can actually work out the equation of that graph. That is a straight line graph, so that's like of the form y equals mx plus b. Now I can work out the gradient here by rise over run. The gradient here is 12 and the run is 6, so the gradient is 2. It's 12 on 6. So it's it's like y equals 2t, and the y-intercept is negative 12. It's like y equals 2t minus 12, but we've got v and t. So it's v equals 2t minus 12. That's the equation for velocity. I mean, if you put when time is 0, velocity is 12. When time is 6 seconds, velocity is 0. So therefore, x is the integral of 2t minus 12 dt, which is 2t squared on 2 minus 12t plus c. Now we know that that is t squared minus 12t plus c. Now we've been told that initially the particle is at the origin, so when t is 0, x is 0, so therefore we get that c is 0. So therefore the equation is x equals t squared minus 12t. Okay, that is the equation for the displacement. That is a concave down curve. If you factorize it, you get t, t minus 12. So over the 12 seconds, it looks like this. Now, sorry, I didn't need to do that. What I could have done was say the velocities, that this has got a negative gradient. Sorry, yes. Wait a sec. And I've drawn the wrong curve, as you can see. So when I was just checking that, see here, gradients negative, 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 positive, zero gradient, sorry, positive, positive, positive. My curve is drawn upside down because it's not thinking, it's concave up. So if you look at that, t squared minus 12t, it's concave up. But they told us that the particle is initially at the origin. So we've got x, it's initially at the origin. And you can see here that the gradient was negative from time is 0 to 6. That's negative values for first derivative velocity. Remember, velocity is dx dt, the gradient of the displacement curve, and it's negative, so it has to go down. And then velocity was 0 at time 6 seconds. So here we've got gradient of the tangent to the velocity curve is 0. And then here velocity is positive, and we can see the gradient here is positive. So this just means for 6 seconds, if I substitute when t equals 6, I can work out what this value is. I get that x is 6t squared, which is 6 squared minus 12 times 6. So it's 36 minus 72, which is negative 36 meters. In other words, I'm just at 36 meters to the left of the origin at time 6 seconds. So we've just sketched the position from the origin over those first 12 seconds. And what we can do is keep it going, because this does look like it's going for longer, definitely longer than 12 seconds. Okay, so that's the graph.